Let's look and see how we can use Venn diagrams in probability. We have a Venn diagram here showing sports played by second years in the Pres in the form 21. Okay, so we have some playing hurling, some playing football, and some playing camogie. Okay, so what's the probability that a student plays all three games? Okay, well, there's only one person in the middle here that plays all three games, so it's 1 in 25. And the probability that a student plays hurling, we add up all the guys in here, and we have 6 and 4 plus 2 plus 1 is 13 out of 25. And that a student plays football, we've 2 and 3 and 1 and 1, so we've 7 in 25. And the student plays camogie, we've 4 and 2 and 1 and 1, and we've 4 and 2, 6 plus 1 and 1 is 8 in 25. What's the probability that a student doesn't play any of the games? Well, from the universal set here, there's 6 people who are outside the hurling, football, camogie areas, so there's 6 in 25. And the probability that someone plays 2 games max, that's these guys here. There's this one, this person, and this person here. Those 7 people only play 2 games maximum. Now, when we look at tree diagrams, we can use tree diagrams in probability. We're basically considering a trial, looking at the outcomes, and we're noting the outcomes in our tree diagram. It should be at the nodes. We should note the possible outcomes at the nodes, and we can mark or mention the actual probabilities along the line from node to node. Okay, so we'll do by example. A family has 3 children. What is the probability that they'll have 3 boys? Okay, well, they're going to have a first child, a second child, and a third child. Okay, so the first child is either going to be a boy or a girl. They are the 2 outcomes from that trial. Okay, and the second child, if they have a boy, is going to be a boy or a girl. It's independent of the first. Or if they have a girl, it's going to be a boy or a girl. Okay, and then the third child, whether they had a boy or a girl, is going to be a boy or a girl. Can 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 be a boy and a boy and a girl and a boy, or a girl and a girl. Okay, so they could have 3 boys, or they could have 2 boys and a girl. They could have a boy, a girl, and then a boy. Or they could have a boy, a girl, and so on. Okay, and there's 2 by 2 by 2, 8 possible outcomes. Okay, so the probability that they have 3 boys is 1 in the 8. It's 1 in 8. Okay. Now let's just, for the fun of it, let's just remove the red marker there, and let's just add the probabilities now. So if they're going to have a boy or a girl, there's a 1 in 2 chance that they'll have a boy or a girl. Same here, same here, same here. So 1 in 2 chance of one or the other each time. Okay, so let's use the multiplication rule, okay, or the AND rule that we had before, where we would say that the probability of a boy and a boy and a boy is equal to the probability of a boy multiply the probability of a boy multiplied by the probability of a boy. So if we take this here, that would be equal to a half by a half by a half, and that's equal to 1 over 8, which is what we got by just examining the sample space, but we can do it numerically as well. Okay, now look at the second example. Two coins are tossed. Okay, so if two coins are tossed, then we've two outcomes, heads or tails by two. First coin, second coin, four potential outcomes. So we toss the first coin, heads or tails. We toss the second coin, we can have a head or a tail, a head or a tail. And there's the sample space resulting from our tree diagram. Okay, but if we put the probabilities on, so toss coins, one or the other, it's a half. 1 and 2, evens chance, it's going to be a head or a tail. Same again, even chance, head or tail, head or tail. Okay, so the chance of getting two heads is a half by a half. It's a quarter. Or of getting a heads and a tail is a quarter, or tails and a head, a quarter, and tails and a tails, it's a quarter again. Now let's look at a tree diagram example with two spinners. Okay, so here's a spinner A, and there's 3 parts shaded, of 3 of 4 parts shaded. Spinner B, there's 2 of 5 parts shaded. Okay, and each spinner is going to be spun once. So let's say we spin. Let's do the tree diagram. Sorry, if we spin spinner A, then the chances that we'll land on a shaded part are 3 in 4, and the chances that we'll land on the non-shaded white part is 1 in 4. Okay. If we were then to spin spinner B, this is spinner A and spinner B. Okay. If we then spin spinner B, the chances of getting shaded are 2 in 5, and unshaded or white 3 in 5, 2 in 5, 3 in 5. So we can work out from the tree diagram the probability of getting a shaded part with the A spinner followed by a shaded part with the B. That's shade and shade. It's 3/4 by 2/5 is 3/10, or 3 in 10. Okay, or the probability of getting the same colours. So that's the probability of getting a shade and a shade, plus the probability of getting a white and a white. So there's the shade and shade, there's the white and the white. So we'll find the probability for each of those and add them. It's 9 in 20. And just be aware there that here, this probability of getting the same colours, that's the probability of shade, shade, or white, white. And from our old rule of addition, the addition or rule, that's the same as the probability of shade, shade plus the probability of a white and a white. And then beneath that, the probability of a shade and a shade is found using the multiplication or AND rule, and the white and a white is found using the multiplication or AND rule. But together, the probability to find one or the other, we use the addition rule. So it's quite a good example in that it shows the use of the two rules as we solve the tree diagram. And finally, just note that all the probabilities here should add to 1 of the possible outcomes, and the order of spinning doesn't change the probability. So if we put B's possible outcomes there followed by spinning A, we would still end up with the same results.